So let's work these out. 10.1 group problems here. Okay, your teacher brings 2 bags of colored goldfish crackers to class. Bag 1 is 25% red cracker, and bag 2 has 35% red crackers. Each bag contains more than 1,000 crackers. Using the paper cup, your teacher takes a simple round sample of 50 crackers from bag 1 and a separate sample of 40 crackers from bag 2. Let it be the difference in the sample proportions of the red crackers. Okay, again, what we're doing here, if you recall from the notes, is we basically got population 1, we got population 2. Those are the 2 different bags of goldfish. So out of population 1, we're going to find a proportion, right? We'll call it proportion 1. And out of population 2, we're going to take a little proportion there. What we're most concerned about, is there a difference between these two? Here, now there might be a subtle difference between those two, but we're hoping that it relates us to what is the difference between the true proportion of population 1 and the true proportion of population 2. Okay, so everything is based on, first, what are the socks, right? What does this new distribution look like? So P1, P2, the shape. So what we say that the shape should always be approximately normal. Why? Because we have some normal checks that we can do. So we're going to go, is n1 times p hat 1 greater than or equal to 10, and is n1 times 1 minus p hat 1 greater than or equal to 10? Because if the first population, the sample that came from the first population, if that represents normal, that's good. And then, though, we have to do a second check. Oh, it's going to be a lot more work here, because now we're going to have to do this again. We're going to just have to double up all our checks. So make sure that population 2, the sample that came from population 2, also is normal. Because if I take one normal minus another normal, you get normal. All right, so both checks have to be normal. So that's what we're going to end up doing here today. I'm doing that without doing the actual numbers there. All right, find the mean of the sampling distribution. Here's what we know, is that we're going to be looking for the mean of all those p hat 1s minus p hat 2s. Remember, we're building this approximately normal sampling distribution, but we are always going to take on the assumption that this is equal to 0. So we are going to put a 0 in the middle of this thing. That's going to be our assumption when we come to our null hypothesis. So you're going to see that phantoms on there. And then standard deviation. Oh my, this is where it gets complex. Here's what I want you to do. I want you to go find your formula sheet. Let's turn to page 2 on the formula sheet. And here we are, standard deviations. Okay, so standard deviations, we're going to really look at this standard error piece. It could take on 2 different roles. It can be this one, which we're going to use sometimes, but it can also be this one, with p hat c being this number here. But when do we use what's in red? When do we use what's in blue? Okay, that's a good question. When P1 is equal to P2, or I guess you could say this, or if P1 minus P2 is equal to 0, if the population proportions are subtracted from each other equals 0, then we're going to be using this one down here. We call this the pooled standard deviation. Otherwise, we just use the one above. Now, I say that because it's going to get complex as we go through this, okay? So here's another thing you might want to write on your notes. We will always use for confidence intervals. We're always going to use the one that I circled in blue for confidence intervals. And then we will always use for hypothesis testing. Okay, so that's what I want you to know for this. It's a lot to take on, I know, but we need to know that this is here, and it's on a formula sheet. So we always get the formula sheet. So let's use the formula sheet to our advantage, okay, when we do that. So that is the standard deviation of sampling distribution. All right, let's move beyond that. Let's do a couple good examples. One confidence interval, 1 is a test of significance, so we can really dial this in. All right, so walk with me, if you will, through this one. A Pew Research Center poll asked independent random samples of working women and men. Are we talking about independent distributions? Yes, we have the women distribution and we have the men distribution. That's 2 different populations. How much they value their job security. Of 806 women, 709 said job security was very extremely important compared to 802 of the 944 men surveyed. Construct and interpret a confidence interval for the, check this out, difference in the proportion. So we know difference in proportion, men and women, 2 populations. Confidence interval, that's what they want us to do. When you hear confidence interval, you think panic. Panic. Especially AIC. The assumptions. Let's get right into it. What are the assumptions? Remember back from chapter 8. We're doing the same assumptions, only we're doing it twice. So I like to create a T-table. Okay? So what I'm going to have my 2 populations. That's my women population. That's my men population. Okay? And then we are going to go for it, right? Here we go. Women. Here are the 2 important numbers. So in 806 times p hat. I better figure out a p hat on this right here. So p hat women is equal to 709 divided by 806. So let me grab my calculator. Let's do this. 709 divided by 806. I get 0.88. Let's call it 0.88. So 0.88, is that greater than or equal to 10? You betcha. 806 times 0.12, is that greater than or equal to 10? Yep. Okay, perfect. So let's do the same thing with men. 802, all right, I'm going to have to do this one now. P hat men. And instead of calling it 1 and 2, I'm calling it M and W, right? It makes more sense to me to use M and W. All right, 802 over 944. So let's do it. 802 divided by 944. 0. Let's call it 85. So I'm going to go 0.85. Is that greater than or equal to 10? Yep. 802 times 0.15. Is that greater than or equal to 10? Yep. Okay. There is our shape check. So both of them are showing approximately normal. Therefore, when I subtract them, the difference, it's also going to be approximately normal. Okay. Independent random samples. So let's do random check. Random check. So the bias, they cleared the bias check. And then we would say working, all working women. Do we believe that there's more than 8,060 working women? I think that's safe to assume. All working men. Do we believe that there's more than 9,440 working men? I would think so. Assumptions check out, people, and they have to be explicitly written out, so do it. Okay, there's the A. On to the I. Okay, here's where we got to get right into the formula. Let me write the generic formula, then I'm going to put real numbers in it, and then we're going to go from there. Here is the generic formula. P hat 1 minus P hat 2 plus or minus. Remember, proportions are always Z, so then we're going to go look up a Z, divided by, this is the big one, right? So again, which one of these standard deviations do I use? Always for confidence interval, because nobody said P1 is equal to P2. Did you see that anywhere in there? Nope, I didn't. So we're doing this. And typically you won't ever see that. So we're always going to be using the top one there. So let's come back to this right here. And we have P hat 1 times 1 minus P hat 1 all over N1 plus P hat 2, 1 minus P hat 2 over N2. So there's your generic formula if you want it. Okay. Let's start putting numbers in there. I'm going to go, instead of 1 and 2, I'm going to go women and men. I'm going to just leave that order as is. So I'm going to go 0.88 because they gave me women first, 0.85 because they gave me men second, plus or minus, Z star. Let's go look up a 95% Z star value. That's 1.960 times, keep writing it out. Here we go, 0.88 times 0.12. Notice how I'm just doing the 1 minus p on that, over, how many was there? 806, plus 0.85 times 0.15 over 944. All right, I got it. I got my interval calculation shown. Time to let the calculator do its work. So here's where I'm going to go in my calculator. I am going to go find 2 for 2 samples, prop for proportion, z, because it's always z, int, which is short for interval. Let's go there. Stat, test, 2, prop, z, interval. Got it? Okay, x1, that's going to be my women, right? So let's do this. Here we go. 709. N1, 806. That's the women. All right, x2, that's the men. That's the way I put them in. 802. 944. Confidence level, 0.95. Calculate. Okay, here is what it gives me. Negative 0.0019. That's the lower bound. 0.06209. There is the upper bound. Lower, upper. You have your confidence interval there. All right, I'm going to stop and pause because the one number that I care most about, and I want you to always think this, is 0 in my interval. All right, I always want you to think that, because if 0 is in your interval, there is a possibility that men and women are the same, that the difference in their proportions equals 0, which would make them the same. 0 is in this interval, so there is a good chance that women and men are the same. Okay, so I want you to just take that into account. All right, let's finish this off with a good old conclusion. Here we go. We are 95% confident the interval negative 0.002 to 0.062 captures the true difference. Okay, there's the important word. Difference in proportions between men or women and men who feel job security is important. Okay, let me highlight true difference in proportions. That's literally what we're trying to find, the true difference in the proportion. I'm 95% confident that it is in this interval. There it is, confidence interval. All right, I want you to take note of which standard deviation formula I used from the table. Also, notice you have to double up on your checks. Yes, twice as much work as you did back in chapter 9. All right, let's move on to the next one. Difference of sample, test of significance. Study long-term effects, preschool programs, poor children, research, design, and experiment. They recruited 123 children who had never attended preschool for low-income families in Michigan. Research randomly assigned 62 of the children to attend preschool and the other 61 to serve as a control group. Check that out. 62 and 61. They have 2 distinct groups, group 1 and group 2, preschool and a control group, no preschool. One response variable interest was the need for social services as an adult. Over the 10-year period, 38 children in the preschool group and 49 in the control group have needed social services. Question, do the data provide convincing evidence? That means run a test, which means phantoms. That preschool reduces the later need for social services in this. All right, now check this out. I do not see the word proportion. I do not see the word means anywhere on here, but I do know that if you give me the number of successes over the number of sample, then I do have a proportion, all right? So let me actually dial in some numbers real quick because we're going to need them. Proportion of, let's go preschoolers, P hat of P equals 38 out of the 62 needed social services as an adult from the preschool group. So 38 divided by 62, 0.61. And let's go P hat of, and I'm just going to little subscript N, non-preschool. Let's see, we had 49 in the control group out of the 61 that were there. 49 divided by 61, 0.80. Okay, that's some things that I see. Remember, this came with a sample size of 62. This came with a sample size of 61. Here's some things I know. All right, let's get into the phantoms. Here we go. Null hypothesis. This is a standard, so don't even try to change it. P, the true proportion of kids who go to preschool should be the exact same as the true proportion of those who do not go to high school. If you like to write it like this, P of P minus P of not equals 0, this works as well. Write it this way, or write it like both. It is your choice. All right, alternative hypothesis. P of proportion, P of no. What do we believe, right? What is the belief? Do these data provide convincing evidence that preschool reduces the later need for social services? So preschool is less than the not preschool. Or if you like to write it like this, preschool minus the not would give me a negative value, or less than 0, right, which would be a negative value. You can write it either way. I kind of like this. I just like the look of this, but you don't have to like the look of it. You can do it your own style if you want, okay? So there's a hypothesis. All right, here we go. Assumption checks. Yes, it takes a long time. I know. Get over it. It's a college level class. Sometimes we got to do a lot of stuff. So I like to draw a little T-table. It just kind of keeps me organized. We got the preschool group, and we got the non-preschool group. All right, here we go. Ready? N 62 times 0.61. Is that greater than or equal to 10? You bet it is. 62 times 0.5. Nope. Let me get this. Let me get my numbers straight. 0.39 is 39% of 62 greater than or equal to 10? Yep, it is. 0.39 times 62. I'm pretty sure it's 24. Yep. All right, let's try over here. 61 times 80%. Is 80% greater than or equal to 10? Yep. 61, 20%. Is that greater than or equal to 10? Yeah, not by much, but it is. It doesn't matter how much it is. It just has to be greater than 10. So these are both going to take on normal shapes independently. So together, it will take on a normal shape. Okay, now this is the deal. Randomly assign. You have to do random. So randomly assign. Yep, that's good. And so if they randomly assign those cats, they randomly assigned these cats. Yep, good. All right, so preschoolers, non-preschoolers, good. 10% rule, typically. But now this is an experiment. So the experiment would always, and this is, we can use this phrase if you want. If you don't want to actually do the 10% on an experiment, you can say this. Assume individuals are independent. What does that mean? That means that when I am running an experiment, a person in my group who received social services, I had nothing to do with that, or I also don't need to receive social services because I am different. I'm independent. So we can use this phrase if you want, if we're talking about an experiment. Otherwise, we need to run the 10% rule. Okay, let's keep going. I'm going to move right to the T part of phantoms. Remember, the T is going to be drawing a curve. In this case, it is going to be a Z curve, Z distribution. Why is it Z? Because proportions are always Z. That's why. Where are we going to center this at? we're going to center the difference, the claimed difference. The claimed difference is 0. This is going to be standard. It's always going to be 0. Always going to be 0. Okay? And so now at this moment, let me take out my calculator. Let's go find 2 prop z test. 2 prop z test. All right, so I'm going to go stat test. 2 prop z test is number 6 on my calculator. All right, let's put in our values. So in each of these groups, remember they're different groups. There's a preschool group and a non-preschool group. So we got 38, that's my x1 out of 62. x2 is 49, and n2 is 61. Okay, we went with a less than sign. That is the middle one there. It's not equals to, less than, greater than. It's the less than. We want P1 to be less than P2. Okay, and now let's calculate. So now I'm going to have some values to use here. I have values to use here. Okay, first of all, what does my z calculation look like? All right, here's the generic z. Actually, let me write the generic z over here so you can put it in your notes. Z is p hat 1 minus p hat 2 minus the claim, which is always going to be 0, over, remember we got to go to here. Okay, which one of these do I use? This one or this one? Well, frankly, when P1 is equal to P2 is assumed. When is P1 equal to P2? Guys, always. That's always the standard claim. And if it's going to be the standard claim, then we're going to have to use the second standard deviation calculation. Okay, so here we go. Generically, p hat combined, 1 minus p hat combined, times 1 over n1 plus 1 over n2. So it's that junk on the bottom. What is p hat combined? P hat combined is all the successes from the first one plus all the successes from the second one over the size of group 1 plus the size of group 2. What does that look like in this? Well, let's do it in this one right here. So what is it? 38 and 49. So we do 38 plus 49 over, what were my sample sizes? Again, they were 62 plus 61. Right? So I could literally do, this is going to be my p hat value. Literally combine those two together. But guess what? My calculator does it all for me. So check this. Let's do the z calculation, but I'm going to pull everything out of my calculator. Ready? P hat 1, which was my preschool group, is 0.61, which we already knew, minus p hat 2, 0.80, which we already knew, minus the claim is 0, over, okay, I need my p hat combined. Here's what go look at your list on your calculator. It gives you z, it gives you the p value, and then it starts giving you other stuff you might want. P hat 1, p hat 2, p hat without any subscript. That is the p hat combined value. So 0.71, 1 minus 0.71 over, now we just need the sample sizes, 1 over 62 plus 1 over 61. Okay, so that's what it would look like. Do I need to actually calculate that out? No, go back and look at your calculator. It already tells you what it is, negative 2.32. Z is negative 3.32. So watch this. I'm going to cheat a little bit, right? I'm going to go here, negative 2.32. Yep. I'm going negative 2.32 standard deviations below the mean. And then, what direction should I be shading? It says less than, so I guess I'm going to be shading less than. Look at that. Smooth little kind of, I call it cheating. It's not cheating. It's just using my resources, right? So there's my matchup there. All right, now I drew the curve. I shaded the curve. I showed the z-score. Now let's go ahead and obtain a p-value. Obtain a p-value. P-value is, oh, it's listed. It's right under the z. 0.0102. Make a decision. You should know how to make a decision at this point. We did it all of chapter 9, making decisions all the time. If my p-value is less than the alpha, then we reject. Guess what? They do not give me an alpha value. So here's what you have to say. I'm going to say reject the null hypothesis at, and let me give you just an alpha value. If I use alpha 5%, if you don't have any other reason, just use 5%. Alpha is 5%. Summary. I mean, technically, you can use anything you want. If you choose to use 1% here, you need to fail to reject because your p-value then is slightly bigger than 1%. Okay? Summary. Since I rejected, we have evidence to suggest that attending preschool reduces, right, less than, reduces the need for social services as an adult. There it is. Again, connect these words. Reject, we have evidence. Fail to reject, we don't have evidence. And this would do it. I do want you to take note of which standard deviation you have to use for that calculation. Yes, you have to double up your assumption checks. Don't forget to draw your curve, shade your curve.